So now we come to the topic of what is known as L'Hopital's rule. So when you've been taking limits, you may have seen a limit that looks something like, say, limit x goes to 0, sine of x over x. Well, if you notice, this goes to 0 over 0, which is not okay because we can't divide by 0. So we're not really sure what this equals. Now, you may have been told that this equals 1 by your professors to do your problems, but let's try to figure out why this should equal 1. Well, whenever we have a limit go to something like 0 over 0, or say plus or minus infinity over infinity, or even 0 times infinity, these limits can't be determined off the bat, so we call them, cleverly enough, indeterminate. So whenever you see one of these as an answer for your limit, this one, or that one, these are called indeterminate forms. And we have to deal with them very carefully because it's hard to tell what infinity over infinity is. Are there different types of infinity over infinity? Could this ever be 0? Could this ever be infinity? Could it be a finite number? That's what we're going to look at. So there's a very special rule called L'Hopital's rule that says if the limit as x approaches some number, this could very well be infinity too, of f of x over g of x equals either 0 over 0 or plus minus infinity over infinity, then we could do something really cool. What we can say is that the limit as x goes to a of f of x over g of x equals the limit as x goes to a of the derivative of the top divided by the derivative of the bottom. So, if our limit is indeterminate, is an indeterminate form, then we can just say the limit of their ratio is the same as the ratio of their derivatives in that limit. So let's see why this is helpful. So let's say we wanted to figure out this sine of x over x deal. Well, like I said before, this goes to 0 over 0, which is indeterminate. So L'Hopital's rule says I can write this as the limit as x goes to 0 of the derivative of the top, and the derivative of sine is, as you know, cosine, divided by the derivative of the bottom. The derivative of x is just 1. So this is the limit as x approaches 0 of cosine of x, but we know that cosine of 0 is 1, so this becomes 1 over 1, which is indeed 1. So in this case, we got our 0 over 0 to be 1. Okay, well, let's see if we can come up with another example of when this would be useful. This comes up quite often when you're dealing with rational polynomials, as you might expect, because we deal with those a lot, and you can take limits of these fractions, but they give us not the best answers sometimes. So, now we're going to look at a case of infinity over infinity. So what we're going to do is look at the limit of limit as x approaches infinity, so we're taking an infinite limit here, of x squared plus 2x plus 1 divided by x to the 4th plus x cubed minus 4. Okay, so if we were to plug this in, you notice that we get infinity over infinity, which again is not a good thing. So we want to use L'Hopital's rule and say that this really is equal to our limit, and we take the derivative of the top and bottom. So the derivative of the top is 2x plus 2 divided by the derivative of the bottom, 4x cubed plus 3x squared. Okay, well, again, we have infinity over infinity. So we're not quite done. So what we can do is we can use L'Hopital's rule a second time. So we just take more derivatives. So the derivative of the top is now 2 over 12x squared plus 6x. Okay, but now we're left with a finite number over infinity. And remember, the golden rule of infinite limits is that the limit as x goes to infinity of any constant over any power of x greater than 1 is 0. Because you get c over a huge number, c over a billion, which is pretty much 0. So as x goes to infinity, we get 0. So we have found in this case that this infinity over infinity has turned out to be 0. Okay, so now that we've seen one example of infinity over infinity, let's do another example. So let's take the limit as x goes to infinity of x to the 5th minus 2 over x squared plus 1. Okay, so if you notice, when we take this limit, we get infinity over infinity. So we have an indeterminate form, so we can use L'Hopital's rule. L'Hopital's rule says that all we need to do is take the derivative of the top and bottom and take that one. So we get 5x to the 4th over 2x. Now notice here, we could just cancel our x's, but let's just keep going to show L'Hopital's rule and how it affects this. So again, this goes to infinity over infinity. So we use L'Hopital's rule. So x goes to infinity. And now we take the derivative again. So we get 20x cubed over 2. So it looks like we have infinity over a constant, which is of course infinity. So we get that this limit actually equals infinity. So now we've had a case where infinity over infinity was 0, and now we have this one where infinity over infinity is infinity. So how can we tell the difference? Well, in general, when you have an infinite limit of some polynomial, a x to the n plus b x to the n minus 1, and so on, divided by, say, lowercase a, x to the m, where m is a different power, plus b, x to the m, minus 1, and so on. There's a general rule. And that rule comes from L'Hopital's rule. You take the derivative over and over until you get to an answer. And the rule is, if n is greater than m, so if the top power is bigger, you get infinity, which is what we found here. The top power was indeed bigger than the bottom. If the bottom power is bigger, then you get 0, just like we found before, because the bottom is going to infinity faster. But if m is equal to n, you simply get the ratio of their coefficients. And all this can be done by using L'Hopital's rule. So now that we've seen how to use this for polynomials, let's move on to slightly more difficult problems. So let's say I want to know the limit of x going to 0 from the right of x natural log of x. Now at first, this may not look like an indeterminate form because it's not in a fraction. But remember, 0 times infinity, or in this case, negative infinity, is indeed an indeterminate form because this is what this approaches. This goes to 0, this goes to negative infinity. So how can we make this look like an indeterminate form to make it look like a fraction to use L'Hopital's rule? Well, if you notice, we could write this as the limit of 1 over x natural log of x. Now, remember, this part, 1 over x, goes to infinity as x goes to 0 from the right. So we have natural log of x, which goes to negative infinity, divided by infinity. Because this can be written as the natural log of x over 1 over x. So we have negative infinity over infinity, which is indeterminate, so we can use L'Hopital's rule. So we now take derivatives. So this is going to be
x goes to 0 on the right. The derivative of the natural log is 1 over x. The derivative of 1 over x is negative 1 over x squared. So remember, dividing is the same by multiplying by the reciprocal. So we have x goes to 0, 1 over x times negative x squared. So we get, this is the limit, as x goes to 0 on the right, of negative x, which is of course 0. So we get that this limit is equal to 0. Okay, so this technique of making a 0 times infinity an infinity over infinity is a common technique you'll use when you have something that's indeterminate but not immediately in the fractional form. So the last example I want to do will show a different property of functions you may have never seen. So the last example is limit as x goes to infinity, e to the x over x squared. So if you notice, this goes to infinity over infinity, so we can use L'Hopital's rule. So this becomes, well, the derivative of e to the x is e to the x over 2x. So we still have infinity over infinity, so we use L'Hopital's rule again. Again, the derivative of e to the x is always e to the x over 2. So that goes to infinity, because now we have infinity over a finite number. But if you notice, even if we were to take the limit as x goes to infinity of e to the x over x to the 1,000, it wouldn't matter. What we would get is that this would always stay e to the x, and then we would just take the derivative 1,000 times, and we would get some constant, which would end up being something like 1,000 factorial. But it's still a finite number. So no matter what power of x you get, this limit, e to the x over x to the n, it's always infinity. But this is true because the exponential function grows much faster than a polynomial. So your exponential would grow something like that, something absurdly quick, whereas a polynomial would only grow like this, much slower. So whenever you're taking limits, be mindful if you have exponentials, because they will end up dominating the limit. This will be very useful when you move on to calculus 2 and do things called infinite series.